to give. That was a failure on my part to get the lab handouts to the website in time for the TAs to get them. Hopefully, since the problems were reasonably short to state, hopefully putting them up on the board was good enough, but I'll try not to let that happen again. Okay. So for the last couple of weeks, we've been talking about a class of languages called regular languages. These are things that are built from sets containing one string by a couple of different operations. You can concatenate two languages. That means you find all ways of concatenating strings from A with strings from B. You can take the union of two languages, or you can compute the Kleene star, the Kleene closure of a language, which means you can pull out any sequence, any finite sequence of elements of the set and concatenate them together into a longer string, including the empty sequence, with or without repetition. And we talked about deterministic finite state machines, DFAs, finite state automata. These are very, very simple computational machines, devices, that you feed a string to one symbol at a time. Every time you feed it a symbol, it changes its internal state. When you're done feeding it symbols, if the internal state happens to be one that the machine likes, it turns on the light bulb and it accepts the string. If the state that it ends up is one that the machine doesn't like, it sounds the buzzer, pulls the lever, and the red chair tips over and throws you onto the floor. So it's a simple machine for taking in a string as input and saying, yes, I like it, or no, I don't. And the sort of fundamental theorem that I've alluded to a couple of times is that these two classes of languages, languages that can be described by regular expressions and languages that can be recognized by DFAs, are in fact identical. This is not in any way obvious, but what I'm going to try to do today is walk you through at least most of the proof. But in order to do that, at the end of class on Tuesday, I need to introduce an intermediate model called a non-deterministic finite state automata, an NFA. And this is the example of an NFA that I showed you last time. It differs from a DFA in a couple of respects. One is that I've got here two different transitions leaving the start state that have the same label. And so if I'm in the start state and you feed me a 0, my future actions are not determined by that input. I have a choice of either staying at S or moving to state A. Somewhat more interestingly, if I am in state A and I read a 1, there's nowhere to go. So what does the machine do? And so the informal description of what it means for an NFA drawn as a graph like this, where you've got nodes for the states, directed edges for the transitions, and every transition has a label, but I no longer have the restriction that exactly one outgoing transition from each state is labeled with each input character. I'll say that an NFA accepts the string W, A1, A2, up to AN, it's the individual symbols, if and only if there is a sequence of transitions Q0 to Q1, Q2, up to Qn, where this first transition is labeled A1, the second transition is labeled A2, and so on. Okay? So the string 0011 is accepted by this NFA because if I'm lucky when I make my choices, I say, oh, 0011, I should go up to A, down to C, then stay at C, then stay at C. If I'm unlucky with my choices, I might instead go stay put at S when I see the first 0, go up to A when I see the second 0, and then have nothing to do when I see the first 1, and so I just blow up the machine. Okay. I could also have done something else. I could have said, remember, 0011, I could have said stay at S, stay at S, stay at S, go to B. And that would not be a sequence, that's a perfectly reasonable sequence of transitions, but it doesn't end in an accepting state. And so that doesn't mean that the NFA rejects, because there's a different sequence of transitions that leads to an accepting state. It just means that's not evidence one way or the other. Where Qn is accepting. Okay? So non-determinism here means I've got choices, but as long as there is a choice that leads to acceptance, the machine accepts. Yes? As far as we're concerned, so the question is there a way to know which choices will lead to acceptance? No. There is no way to know that. It's an arbitrary graph with arbitrary labels. So one way to think about this is when you're running an NFA, if you want to think of this as a physical machine, if you're running an NFA and you're sitting at state S and you see a 0, a little birdie will land on your shoulder and tell you you should go to state A. And as long as there is a little birdie that gives you the right advice, you're happy. Okay? Now, generally, we're scientists, we're engineers, we don't like magic. So the metaphor that was used when I was a student is when I'm at state S and I get 0 as an input, I fork off a parallel universe. And in one universe, I stay at S, and in the other universe, I move to A. If I'm ever in a state where there is nothing to do, I'm in state A and I read a 1, I destroy my universe. I don't exist anymore. If any existing living version of me ever sees an accepting state, I'm happy, I accept. If I finish reading the input and I'm not in an accepting state, I destroy the universe. So if I survive, then I'm happy because I'm in an accepting state and I followed a valid sequence of transitions. Now, creating and destroying new universes is slightly outside the scope of this class, but a more modern way of thinking of this is you're just creating parallel execution threads. If you think of this as an algorithm, when you're at S and you read a 0, you fork off a new thread. And in one thread, you stay at S, and in one thread, you stay at A. If your current thread is at state A and it reads a 1, the thread kills itself. And then finally, at the end, you have a gather phase that did any of the threads succeed? If so, then my global algorithm will report success. Otherwise, my global algorithm will report failure. Okay, so the important point is that this is, really about the existence of a correct set of choices, the existence of one parallel thread out of this forking process that leads to an accepting state. This is not the only model we could have used of non-determinism. I could have changed the definition and said, actually, all the execution threads have to lead to an accepting state. That would have been a different type of machine. It turns out those machines also accept regular languages. But this is the standard one. If there is a correct choice, you magically make it, or said differently, if there is a correct choice, then by exploring all possibilities, you will eventually find it, and you'll accept. So if I think again, I'm going to go through this machine again with my example, just to see what happens. So I start at state S. I read a 0, and I either stay at S or I go to A. At this point, I read another 0. If I'm in S, I either stay at S or I go to A. And if I'm at A, I go to C. At this point, I have a 1, so I either stay at S or I go to B. If I'm in state A, I die. If I'm in state C, I stay in state C. And then finally, if I see a 1, I either stay at S or I go to B. If I'm at B, I go to C. If I'm at C, I stay at C. Because C is an accepting state, this machine accepts the string 001. Here is one of my threads that died because I didn't have anywhere to go. Now, there's a formal way of defining this with notation, and it's useful to have the formal notation down just so that we have some common language to think about. If there's any confusion in my informal description, we'll always have mathematics to fall back on. My NFA consists of a set of states. I have to specify an input alphabet. I have a start state. I have a set of accepting states. And I have a transition function that takes a current state and a symbol and returns a set of states that if I'm in state Q and I read symbol A, these are the states that I could go to. And for example, in this particular case, gamma of S comma 0 is the set SA, and delta of A comma 1 is the empty set. I won't write the other ones down. And so I just say, for every state and for every symbol, where could I go? And then, just like for DFAs, you can extend this to, instead of looking at individual characters, you can look at strings, where I define the transition function using what you would expect from the recursive definition of a string. There are two cases. Either the string is empty or the string is not empty. If the string is empty, then I stay put. I have to put the braces around it because the output of this function is a set. Even if it's a set with one element, I still have to remember that it's a set. Otherwise, I take the union over all states that I can get to from Q reading the first symbol in W, and then I recursively go from each of those states and follow it out along paths determined by the string X. And then finally, the language accepted by my NFA is the set of all strings in the input alphabet, such that when I start at the start state and I read the string, I end up in a set of states that includes at least one accepting state. Okay? This is all the formalities. And this is pretty much where we left things at the end of lecture on Tuesday. So hopefully, if the formalism doesn't make sense, fall back on the intuition. We need to go back to the formalism occasionally because I'm going to be, you know, playing with the model a bit, and we need to have, you know, an agreement on what we're actually doing. That's why we have formalism at all. But the intuition is just, if I can find a path that leads to an accepting state with the right label, then I'm happy. Otherwise, I'm not happy. Okay? Good. So the first thing to notice is that with very, very minor, essentially notational differences, every DFA is an NFA. Remember that a DFA, the transition function returns a single state. I can turn it into a DFA just by putting braces around that state and calling it a set. Otherwise, there's no difference between the two. So an NFA where the transition function always returns a set of size 1, the behavior of that machine is in fact determined by the input, and so, okay, it's a DFA. There's minor notational difference just because I need to do something more general here. Okay, so every DFA, right, so every DFA is an NFA. So in order to prove that DFAs and regular expressions are the same thing, I need to prove 3 more things. First, for every NFA, there's an equivalent DFA. Going one direction, allowing myself more freedom, that's just trivial. I have more freedom, I just didn't use it. Okay, fine. Allowing myself less freedom, where I have to actually determine my actions at every state for every symbol, it requires some work to show that restricting myself that way doesn't change what I can do with the model. It changes what I can do with the model efficiently. Turning an NFA into a DFA can exponentially blow up the states, but for now we're just trying to show that these things accept the same sets of languages. The second thing I need to show is for every regular expression, there is an equivalent NFA. Now, I could have said there's an equivalent DFA there, but I don't really have a good way of going directly from a regular expression to a DFA, except going through this intermediate state. So let me write these down. What's left? I need to be able to go from an NFA to a DFA. I need to be able to go from a regular expression to an NFA. And finally, I need to be able to go from an NFA to a regular expression. Okay, so these are the 3 things that I need to talk about during the rest of the lecture. The first 2, I'm pretty sure that I can cover completely. And these are simple enough that you can reasonably execute them by hand for reasonably small NFAs and reasonably small regular expressions. The second one is essentially you just parse the regular expression and write some arrows down. The first one is definition chasing. The third one, going from an NFA, or I could start with a DFA here actually, to a regular expression. Again, this is not too difficult to understand in principle, but every step in the NFA to regular expression algorithm blows something up by a constant factor. And so you end up with regular expressions that are exponentially long, which means this is not something you necessarily want to do by hand. I'll try to give one example for something small, and you'll see the exponential blow-up happening. I'm not sure that I'll be able to get through all of the details of part 3 here, but for those who are interested, I'll try to give the intuition. Those who are interested in the details, I'll refer to the notes. All right. And so the implication of this is going to be a language is regular if and only if it's accepted by a finite state machine. Okay. So I think it's actually a little bit easier if I start with number 2. Go from a regular expression to a DFA, or to an NFA. And the construction of an NFA from a regular expression is going to be described in the only way that it can be, which is recursively using the definition of a regular expression. Remember, a regular expression is either the symbol meaning the empty set, it's a single string, it's a something plus something, or it's something dot something, or it's something star. And so for each of those cases, I'll do something to build either an NFA as a base case or by combining smaller NFAs into larger ones. But there's one particular thing that shows up almost immediately in the base case, which is one of the things that a regular expression can contain is the symbol epsilon, meaning an empty string. And it'd be really nice to have something in the DFA that explicitly corresponds to an epsilon. Similarly, when you're designing an NFA from scratch, sometimes it's nice to be able to design independent components and then say, you know what, I can jump from this part to that part freely without consuming any input symbols. And so I'm going to slightly generalize my definition of NFA by allowing an additional type of transition called an epsilon transition. Okay, so there is an NFA. It accepts all strings that contain either the substring 0, 0 or the substring 1, 1. It's the same, it accepts the same language as the 4-state DFA that I was showing you earlier. What are the rules here? Without writing down the formalism, an NFA with epsilon transitions accepts a string W if and only if there exists a sequence of transitions that starts at S, Q1, Q2, la 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 la, up to Q sub L, no longer necessarily Q sub N, where two things are true. One is W is the concatenation of these labels on the transitions, and each A sub I is either equal to epsilon or it's a symbol in the alphabet. So once again, let me start with my symbol 0, 0, 1, 1, and show you how this machine could accept this string. Right? So I'm going to start at S, and I'm going to read my first 0, and I'm going to stay at S. And then I'm going to read my second 0, and I'm going to stay at S. And then I'm going to follow an epsilon transition to D. And then I'm going to read a 1 and transition to E. And then I'm going to read a 1 and transition to F. Then I'm going to read nothing. I'm just going to transition to C for free. And then finally, I'm going to transition to G for free. And that's an accepting state. So when I'm in a particular state in this NFA, I have a choice of two things that I could do. If there's an arrow leaving the state for another one that has an epsilon on it, sure, I just follow it. And that does not consume anything from the input. The other possibility is I can say, what's the first thing on the input? Oh, it's a 1. Okay. I can look for all of the 1s leaving my current state, and I can pick one of them and follow that. I can do, so I have a non-deterministic choice of whether to follow an epsilon or to follow a character transition. And in either of those, I also have a non-deterministic choice of which epsilon to follow or which symbol transition to follow. Okay. Now, that means when I want to define this thing, my transition function is no longer just going to be q cross sigma, but rather I'm going to have a slightly larger alphabet to formally define my my transition function. Okay. Now I claim that this, if I allow myself epsilon transitions, that gives me more flexibility, which means when I'm designing NFAs, it's useful to say, you know what, I'm going to design my NFAs with epsilon transitions because that just makes life simple. I don't have to worry about exactly making the last part of this component and the first part of that component match up. I can just transition for free. But I claim that, in fact, you're not giving yourself any more power in terms of what you can accept. That any NFA with epsilon transitions can be transformed into an equivalent NFA with the same, with essentially identical behavior, but with no epsilon transitions. Can anybody suggest how I might do that? Yeah. Okay, so this is a good idea, and it almost works. The suggestion is, if two states are joined by an epsilon transition, just merge the two states. Okay? The problem with that is that I'm not sure it's apparent in this particular example. Look at the states labeled C and D, the upper right corner and the lower left corner. If I'm in state D and I read a 1 and I stop, that's not an accepting state. But if I'm in state C and I read a 1 and I stop, well, what can I do? The only thing I could do in that case is follow an epsilon transition somewhere. Say I follow an epsilon transition to G, and then I read my 1, I stay in state G, and I accept. So starting in state C, it's possible to accept symbol 1, the input string 1, but starting in symbol D, it's not. So those two states are not, in fact, equivalent. Now, if I'd had one more transition here, say here, with an epsilon on it, now those three states that have a cycle of epsilons, those really are equivalent, because if I find myself in any one of those states, I know I can just magically transform myself to any other. But if I don't have cycles, different things that are joined by epsilon transitions may not actually be equivalent. So I need to be a little bit more careful about this. Yeah. Okay, so the question was, we talked about subsequences in a previous homework, and I think possibly in a previous lab. Is there any connection here? One way to see this is that you have this sequence of transitions that has a label made up of epsilons and symbols. The input string has to be a subsequence, and everything else has to be an epsilon. But otherwise, that's pretty much the only connection. Yeah. Good. So here's the idea. The question that I want to ask when I'm designing an NFA is, if I'm in state B, or I'm in state C, or yeah, I'll say I'm in state B, and I read a 0, where can I be next? And the suggestion is, well, first I go from B to C, but then there are epsilon transitions I can follow. I could just follow them all. So from B, I can get to either C or D or G by following a 0 and then some epsilons. That will work, but then you actually run into, except for one thing, you run into some problems of how do you start? Because the way I defined an NFA from the beginning, and this was a choice based on what everybody does, there's not really any real reason for it. NFAs have a single start state. I start in state S. So instead of saying, let's do the real transition and then as many epsilon transitions as we want, I'm going to flip it around. So when I'm in state S and I read a 0, what I'm going to do is follow a bunch of epsilon transitions and then follow a 0. And so what that means is that from state S, reading a 0, I could go, well, reading an epsilon, I could get to D, and then reading a 0, I don't go anywhere. I could, from S, read an epsilon here, read an epsilon there. So one transition I could add is this one. So if I'm in state S and I see a 0, I could follow an epsilon transition to D, and then an epsilon transition to A, and then the 0 transition takes me to B. So I'm just going to short circuit that. I'm just going to say, if you read a 0, starting at S, one of the states I could be in next is B. So if I want to talk about this somewhat more formally, I need to talk about the idea, the concept of the epsilon reach of a state. This is all states that I can get to from Q, all states reachable from Q by epsilon transitions. Okay, so in particular, the epsilon reach of S in this particular example is S, D, A. I can get from S to S by following 0 epsilon transitions. I can get from S to D by following 1 epsilon transition. I can get from S to A by following 2 epsilon transitions. Okay? And so the idea now is I'm going to define a new function by saying essentially, let's see, Q and A. The first thing I'm going to do is go to all the states of my epsilon reach, and then from each of those states, I'm going to go out one more step to A. So the way to write this down formally is for all states P in the epsilon reach of Q, I'm going to take the union of that reachable set. Okay. All this says in somewhat less flowery notation is, if it's possible to put in shortcuts by going, if you can replace epsilon, 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 epsilon 0 with just an arrow going straight there labeled 0. Epsilon, epsilon, epsilon 1, you just put an arrow there directly labeled 1. And then what you end up with, I didn't copy into the notes, so okay, let's figure out what we end up with. Start. Thank you. Okay. So there's my original NFA with epsilon transitions, S, A, B, C,
G, which is still accepting state, D, E, F. Okay, when I read a 0 from S, I can stay, let's see, the epsilon reach of S consists of these three states. So when I read a 0, I can go to anywhere that has a 0 arrow coming out of one of these three blue states. So I can either go to S or I can go to B. Likewise, if I see a 1, I can go either to S or to E. Now, if I want to look at what can I get to from A, the epsilon reach of A is just A. So if I'm in state A and I read a 0, I can only go to B. If I read a 1, I killed the universe. If I'm in state D, my epsilon reach is dA. So if I read a 0, I can go up here, and if I read a 1, I go over there. If I'm in state B, I don't have any epsilons at all. So that stays put. If I'm in state E, I don't have any epsilons. If I'm in state C, my epsilons either go to G or to D. If I'm in state C, then I can either go to D or to G. And so from here, if I see a 0, from C itself, I can't go anywhere. From D, I can't go anywhere. And from G, I can stay at G. So when I do this transformation, I add a 0 transition there. Likewise, from these three places, if I see a 1, from C, I can't go anywhere. From D, I can go to E. And from G, I can stay put. And so I have 1 transitions going like this. From F, I have 1 transition here, and either a 0 or 1 transition there. And then finally at G, I have either a 0 or a 1. Okay, so when I remove all the, when I short circuit all of the epsilons, this is the state transition graph I get. And hopefully I'm reading your mind when I ask this next question. Is this right? Is this done? Is this actually an equivalent NFA to the one that I started with? Yes? Oh, thank you. Oh yes, from C to B, there should be a 0. Did I miss any others? Okay, I'll have to fix the notes because I missed it in the notes as well. So, does this NFA accept exactly the same strings as this NFA? I'll give you a hint. I asked the question. No, good. The obvious answer is yes, because I just told you this brown thing. I must be done because, you know, time. No, we're not done. And can anybody say why we're not done? What could happen in the DFA on the left that would allow me to accept a string that I would not accept on the right? Okay, 0, 0. Let's watch what happens. One possibility is I stay at S. One possibility is I go S and then I go up to B. One possibility is I go epsilon, epsilon, 0, 0, and then epsilon into the accepting state. Whereas over here, 0, 0, I can get to S, I can get to C, I can get to B, but there's no path leading from S to G that's labeled with just 2 zeros. So remember, the condition for accepting is that I have any sequence I want alternating between real symbols and epsilons. And when I did this transformation, I took care of all the epsilons that came before real symbols. But that means I didn't handle those epsilons at the end. So I still have a little bit of work to do. How do I do it? Yeah.
Exactly. I'm just going to declare any state that has an accepting state in its
Epsilon reach is accepting. If I'm standing at C and say, you know, if my input's done, I could accept now because I can go over to G with an epsilon. Right? And this actually completes the transformation of the
NFA. I need to define a new set of accepting states. This is the set of all states Q such that the epsilon reach of Q has a non-empty intersection with A.
The high-level TLDR to take away from this is, yeah, you can use epsilon transitions. It doesn't really change anything. When you're designing NFAs, it's really helpful to have them because it keeps you from having to say, instead of two states that I really want to be the same, I can just put epsilons between them instead of having to bend the drawing around to put them in the same place. When you are taking an NFA as input to some other transformation algorithm, on the other hand, you can freely assume without loss of generality that there are no epsilon transitions because there's an algorithm to get rid of them. So when you're designing, you give yourself as much freedom as possible. When you're trying to transform something given to you, you put as many restrictions on that thing that you're given as possible. I realize this is a bit complicated, and it's a bit hard to sort of wrap your head around the idea of, well, there's a magic birdie that tells me whether I need to read input or not. Again, I want you to think about this in terms of parallel execution threads. If I'm standing at this state S, and before I read a character, I could say, you know what, spawn off a thread that takes this epsilon transition. And then again, spawn off a thread that takes that epsilon transition. And then all of those threads simultaneously read. Questions about epsilons? Yeah. The universe ceases to exist.
So you can't go further.
That's the end. That's right. Think about this as a physical machine, right? I have a box filled with gears and a crank that I turn, and every so often I drop marbles into the top, either a marble in the 0 part or the marble in the 1. And based on where the gears are, the gears move to different places, and the marble falls out the bottom, and then the box is in a different internal state. If the box inside is in state B, and I drop a 1 marble in, I break the machine. It falls apart. Okay? And if it just so happens that every parallel thread of your execution, your machine falls apart, then your machine is going to reject. As long as one machine survives to the end and ends up in an accepting state, then you accept. Yeah. Okay, why is there a 0, 1 from C to G? Because when I'm in C, I can go epsilon 0. When I'm in C, I can go epsilon 1. When I'm here, I can go epsilon, epsilon 0. I can go epsilon, epsilon 1. Yeah. Oh, we could. We could. But remember, what I'm describing here is a mechanical algorithm that takes an arbitrary NFA that has epsilons in it and returns an equivalent NFA that has no epsilons in it. Now, that's not the end of the story. Once you're here, of course, you can actually collapse these 3 states down to 1. You notice there's no way to get into A or into D, so you could throw those states out. And if you did that, what NFA would you get? This one, right? So, this is sort of a deliberate choice that I made things more complicated than they needed to be just so I could show off the algorithm in action. But the output of this algorithm, or in fact, the output of any of the algorithms we're talking about, can be further simplified. But for right now, we're just trying to show that these two classes of machines are the same. Yeah. C to D. How do I get from C to D with a 0? Right, so there is an epsilon transition from C to here, but if I'm in C and I read a 0 and I want to read a 0, I could stay put and read a 0, universe destroyed. Or I could transition down here and read a 0, universe destroyed. Or I could transition to G and read a 0, stay at G. So the only 0 error leaving here goes to G. Oh, you're right. 0, boom, boom, goes up to A. Read a 0 goes to B. That was the arrow that I was missing before. That's why this arrow exists. That backward arrow from C to B is epsilon, epsilon 0. Yes, in the back. From F to B. Sorry, say it again. From F to B. Because I have no way of getting from F to A by epsilons. Oh, I do. Oh, crap. I can go, you're right, I can go epsilon, epsilon, epsilon 0. Okay, so, whoop, 0. Thank you. Okay, last question about this, and then I need to move on. Yes, the state is always in its own epsilon reach. So the epsilon reach is everything that I can get to from state Q by following a sequence of epsilon transitions. A sequence of epsilon transitions is either nothing or an epsilon transition followed by a sequence of epsilon transitions. All right, good. So epsilons are good. You can get rid of them if you want to. Let's move on. All right. Yeah, I think actually doing the regular expression to NFA at this point is probably a little bit better. Okay, so if I'm given a regular expression, I believe this was Ken Thompson in 1971. Described an algorithm that can take an arbitrary regular expression and turn it into an NFA. And it really is just recursive definition chasing. Right? So Thompson's algorithm takes in a regular expression, and when, as always, when I say given a regular expression, you should interpret that as I've actually parsed the regular expression, so it's really an expression tree. I'm just using regular expression notation because it's more convenient. It computes an NFA M such that, let's call this regular expression R. The language accepted by the machine is the same as the language represented by R. I'm going to add one more condition because it will help with the induction hypothesis. M has a unique accepting state that is not equal to the start state. Okay? So, proof. Let R be an arbitrary regular expression. Assume that any proper subexpression of R, call that S, there is an NFA, M prime, that has the same language as S, and that NFA has a unique accepting state distinct from its start state. There are 5 cases to consider, mirroring the definition of regular expression. R is empty. R is a single string. R is A dot B, where A and B are smaller expressions. R is A plus B, where A and B are smaller expressions.
and R is a star, where
A is a smaller expression.
here then are the NFAs that I'm going to build for these examples.
When the regular expression is just the symbol empty set,
By definition, I need a start state, and the target I'm going for,
I need an accept state that is distinct from the start state, and there is my NFA. If you read the empty string, well, you can at least be happy that the universe didn't go away, but you don't accept it. If you read any non-empty string, the universe goes away. Either way, you don't accept the string. So the set of strings that's accepted by this NFA, where the transition function always gives you the empty set, is the empty set, the empty language. Okay, so what if the regular expression is a single string W? Well, there are two possibilities based on the recursive definition of a string.
So one possibility is that W is epsilon, and one possibility is W is equal to A times X. When W is equal to epsilon, I have
An epsilon transition.
When W is equal to A times X, I have an A transition. And then in this little box,
By the inductive hypothesis, there is an NFA that accepts only the string X. It has a unique start state and a unique accepting state, different from its start state. So I glue that in here.
right? So this part of the machine,
It comes from the inductive hypothesis, from the recursive definition of strings. Now, in this case, I could have done this explicitly. I could have said, okay, if I've got a non-empty string, I write down the sequence of symbols, and I just turn that into a sequence of transitions, and I get a linked list where each of the edges is labeled by a symbol. That works perfectly well. This, if you expand out the recursion, means the string 0, 0 will give you 4 states, one with the first transition 0, then a transition 0, then an epsilon transition to the accepting state. When you're doing this in the homework in the labs, just write out the sequence. You don't need to really do things recursively all the time. Okay, so if my regular expression is the concatenation of two smaller regular expressions, then by the inductive hypothesis, there is a machine that accepts A, and there is a machine that accepts B, and so I glue them together in series. Okay? Any path from the start state of this machine to the accept state of this machine must go through this intermediate state. And therefore, that path can be divided into an accepting path through A and an accepting path through B. So the string, the label of that path can be turned into the label of an accepting path through A. That's a string in the language of A. And an accepting path through B, that's a string in the language of B. Yes? So I could do it that way. I mean, in fact, the way that I had it in the notes until about 12 hours ago was this. And I may be ultimately convinced that I need to turn it back into this. But this is certainly safer because you want to be sure there aren't any extraneous things going through that. In fact, actually, now that I think about it, let's do it this way. Let's stay safe. Sorry. Yes. I could, but I don't need to. Right. In particular, the way that you would normally do like a union for a DFA is you would build the product construction. But the way you do a union for an NFA
is a little bit simpler. Okay, so I have a machine that accepts A, and I have a machine that accepts B, and I have a start state, which I'm going to connect to the A with epsilon transitions, and an accepting state, which I'm going to connect with epsilon transitions. Again, these two boxes are exist by the inductive hypothesis.
This shows you one reason why NFAs are indeed more powerful than DFAs in terms of design, is that normally if I wanted to accept the union of two languages that are described by DFAs, I'd have to build this big product construction. But with an NFA, I can just say, well, I don't know, a little bird is going to tell me whether I should do A or B. Oh, there it is. Any path from the start to the end is either a path through A from start to end, or it's a path through B from start to end. Okay. And, well, you can probably already see what I'm going to do for this one. Although, again, now I think was a little bit too aggressive with simplifying things. I'm going to have to go back and fix that. So here is my NFA for A. Here's the start state on the left and the accepting state on the right. Ignore the stuff in the bottom right corner for now. How would I turn this into an NFA that accepts A star? Okay, so one idea is let's keep this as an accepting state and add an epsilon transition going back. Am I done? Why not? Right, so the reason that I'm not done here is this won't accept the empty string. The empty string is part of A star. So just to be on the safe side, I need some way to get from the start state to the accepting state. But this, it turns out, actually, despite what I've drawn in the picture, and I have to apologize for that, this turns out to be a little dangerous because there may be other reasons to go into this state, and I don't necessarily want to jump to the accepting state right away. Right? The start state isn't like the only reason I'm in the start state is because I'm starting. It's just a state. So if I end up in the start state, if I had a direct transition here, if I ended up in the start state for some other reason, I might prematurely accept. I don't want to do that. So what I'm going to do is deliberately just say either epsilon or repeat myself. And if I'm really actually being careful, I probably ought to do this. Same reason. Yeah. Remember, the accepting state, the inductive hypothesis says the accepting state and the start state are different. It's mostly, I mean, I could start at the accepting state and put an epsilon transition back to the start. But then the inductive hypothesis wouldn't apply and my pictures would get more complicated. I need epsilon transitions anyway for other things. All right. So except for the simplifications that I made, which are incorrect, and I apologize, I will take those back out of the notes. I was woke up this morning at 5 in the morning, say, wait, I can make it simpler. Wake up at 5 in the morning and say, wait, I can make it simpler? No, it's 5 in the morning. Wait, yeah. That's right. When in the homework and in the lab tomorrow, which is actually on the web now, It asks you to run Thompson's algorithm to get an NFA. What I really want is you to do the brute force thing as described in the notes, and by the time the day is over, the notes will be correct. So what's in there now is a bit too aggressive. It's not actually correct, and I apologize for injecting that bug. But yes, I want you to execute the algorithm. Don't do any additional simplifications. Except the one thing that that is okay to do is if you have a string, you can just say transition, 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 transition. Because the algorithm, as formally described, would have epsilons at the end and possibly even in the middle. Yeah. Yes. These two states are, in fact, the same state. I mean, I could merge them and it would not do anything. This state, I don't want to merge with the accepting state, right? But I'm drawing it this way rather than just having a single arrow going into the accepting state, because earlier in the algorithm, I assumed there's a start state and an accepting state and they're different. So the only reason that I'm making this state, those two states, separate states is to satisfy the induction hypothesis. Okay. So if you play with this for a while, you'll realize what's actually going on here is you're literally just taking the parse tree. You can almost read the parse tree here. So here is a top-level node with a plus, and there's a 0, and then this sequence is nodes that are concatenation nodes, and this loop here is a node that's a star with a 0 hanging below it. And you can actually, there are versions of Thompson's algorithm that say, first, draw out the parse tree, then move these edges around, add some loops, add some epsilon transitions, and the picture is what you want. Yes? Oh yes, you're right. There's a big star around the whole thing. Thank you. Okay. So this gets you from regular expressions to NFAs. And we can get rid of the epsilon transitions by a different algorithm, but it would make the picture a little bit uglier, so I'm not going to do that. Now the question is, how do you get from an NFA to a DFA? Right? And then ultimately, how do I get back to a regular expression? So to do that, I'm going to talk about what's called the subset construction. And here, to keep things simple, I'm just going to say no epsilons, because I know I can get rid of them anyway. So remember, the definition of an NFA is I have these lovely components. In particular, I have this transition function that takes a state and a symbol and gives me a set of states that I could go to next. Now, the intuition that I actually want you to have when you're thinking about the subset construction is from this picture here. Now, I'm going to describe this picture in a different way. It is really, the subset construction you should really think of as more of an interpretation of what the data structure is representing, rather than as there's a sort of fundamental difference in the objects. So there's my NFA sitting up at the top. I read the string 0, 0, 1, 1, and which state I'm in is not determined by the input. I have options. I have choices for what to do. I get this branching structure for the possible states I could be in. And in the end, I just want to know whether there's a path that leads to something accepting. I'm going to say it differently. Instead of thinking about the state I'm in, let's think about the set of states I can be in. Okay? initially, I can be in the set containing, the only state I can be in is S. Given that I can only be in the state S, when I read a 0, the states I can be in next is determined by the transition function. The set of states I can be in next is S comma A. Next, I read a 0. The set of states I can be in, given that I started in either S or A, the set of states I can be in next is determined by the transition function. It's SAC. Then I read a 1. The set of states I can be in next is determined by everything. It's the set SBC. Then I read a 1. The only states I could be in are SBC. So it's true that if I think of the states as those little circles, the state sequence is not determined by the input. But if instead I say, all right, Dr. Horrible has created this NFA. He says, you can't tell what state it's in, blah, ha, ha, ha. And I say, okay, look, I'm going to describe from over here, staring at the black box on the table, a state of that machine is a set of what Dr. Horrible calls states. Okay, now, this is a bit mind-bending because now I'm using the same word to describe two different things. Right? So let's say, instead of a state, let's call it a configuration. Configuration of an NFA is a set of states that the NFA could be in. Given a configuration and a symbol, there is a unique configuration that follows. If my current configuration is, I don't know, S or A or C, and I read a 1, my new configuration is, I don't know, S or B or C. But the transition from one configuration to the next is completely determined by the diagram. Okay. Now, those configurations, there's a finite number of them. In this case, there are 16. Any possible subset of those 4 states could be a configuration of this NFA. So I have a finite state of things, finite set of things, and I have a transition function that takes a thing and a symbol and it gives me a new thing. It's a DFA. Okay, so let's go through this a little bit more carefully. All right, so suppose I'm given an NFA in these objects. I'm going to define an equivalent DFA. So the new set of states for my equivalent DFA is the set of all subsets of states of my original NFA. DFA states are sets of NFA states. Input alphabet doesn't change. The starting configuration for my DFA is, well, the only state, and the only NFA state I can be in is S. So my DFA state is a set containing the single NFA state S. My accepting DFA states, this is the set of all subsets of Q such that A intersect that subset is non-empty. If I'm in a configuration that includes some accepting NFA state, I'm happy. I've found myself, there's a way to get the NFA to accept. Okay? And again, this is just the same, looking back at the picture here, the final configuration of this NFA is the set SBC. And because C is an accepting state, I like this configuration. Okay. And then finally, given a DFA state and a symbol, what new DFA state do I go to? Well, remember, a DFA state, Q prime, that is a set of NFA states. From each of those NFA states, I have a set of things that I can go to by reading A. So what I want, then,
is the union over all NFA states in this subset of what I can get to from that NFA state
by reading that symbol. Okay. There's my NFA on the left. Here's a bunch of Greek letters and braces and in strange Unicode LaTeX symbols that define the corresponding DFA. The important thing to remember is
that a DFA state is a set of NFA states.
And everything else just follows by, well, what happens when if I have a set of NFA states that I could be in and I read a symbol, what set of NFA states could I be in next? If I'm in one of a set of NFA states, is that a good set or not? Okay? And so if I do this, apply this algorithm to this nice innocent 4-state NFA, what I'm going to get is a 16-state DFA. And that 16-state DFA is horrible. Okay? This is the only time that I spent far too long drawing this picture. One of the things you'll notice is that some of the states are in gray. Those are the ones I can't get to from the start state. So this is one of the things that happens when you apply the subset construction literally, is that you end up with a DFA that is provably equivalent to the original NFA, but it's huge. It's got a whole bunch of stuff in it that isn't necessary, either because you can't get to it at all, or even if I get rid of all the stuff that's in gray and just focus on these 5 yellow states, you might be able to shrink this further, maybe. No, in this case you can't. Okay? But you might be able to. So the subset construction gives you really awful DFAs. Mostly because lots of the states are not going to be reachable. Now, not all the time. Sometimes you get an exponential number of states and they're all reachable, which means they all really have to be there. But sometimes you get things that are not reachable. And so why did I bother to write them down? Okay. So the last thing that I want to say very briefly is how you would make this work if you didn't want to write down all of this other stuff. So there's an incremental version of the subset construction that instead of just writing down all the states and then writing down all the transitions, you say, okay, I'm going to start in this DFA state. And then if I read a 0, I should go to that one. And if I read a 1, I should go to that one. These are new states I haven't explored yet. If I start here and I read a 0, I should go to that one. If I start with there and I read a 0, I should go there. Or I read 1, I go there. Here are new DFA states that I haven't explored yet. And so essentially what you're doing is you're performing a traversal of the DFA graph without constructing the DFA graph in advance. You're exploring the DFA graph in order to write it down explicitly. So here's how that algorithm goes. This is the so-called incremental subset construction.
And this will be the last thing I'll have time to talk about. So I need to write down, and again, this time I'm actually going to do things with epsilons. I'm going to write down a table that has 5 columns. The DFA state, the epsilon reach, what I transition to with a 0 and a 1, and whether that DFA state is accepting.
And I'm going to start by, when I write down my DFA states, there's sets of NFA states, but I'm going to leave out the braces and the commas. I'm just going to write down just a string of letters. So for this particular NFA, I start by saying, well, I have to start in state S, NFA state S. When I'm in NFA state S, the epsilon reach is SDA. So with my epsilon reach. And then if I'm in any of those three states and I read a 0, where can I go? Well, from S, I can go to S. From A, I can go to B. And from D, I can't go anywhere. So the delta prime here is S, comma, well, I said I wasn't going to write down commas, is SB. Similarly, if I read a 1, I can either, from S, I can get to S. From A, I can't go anywhere. And from D, I can get an E. And this epsilon reach doesn't intersect any accepting state, so the answer is no. I've discovered 2 new states that I haven't seen before, so I'll write those down. And then I do the same thing over again. From SB, the epsilon reach is SABD. And from any of those 4 states, I write down what you get with a 0, what you get with a 1, and whether it's an accepting DFA state. And as I do this, every time I fill out a row, if I discover new states in the 3rd and 4th column that I haven't seen before, I start a new row. And if you walk through the that construction for this particular NFA with epsilon transitions, this is what you get. Starting at S, I go to the epsilon reaches SAD, 0 I go to SB, 1 I go to SE. Starting at SB, my epsilon reaches SABD. Start at 0, from 0 I can go here, from 1 I go there. And I just literally did this by hand. And then once I had this table, here I can draw this picture. Now, this picture is horrible, it's ugly, it's terrible, it's no good. But think about what you would have gotten for the regular subset construction for this thing. This NFA has 8 states. So the standard subset construction would give you a DFA with 256 states. In comparison, this is pretty good. And then finally, you can actually do this with the Thomson NFAs. And you actually tend to get reasonable things. So you get reasonable DFAs out of your regular expressions. Okay, thank you for hanging out. I'll see you on Tuesday.
How do I understand the states in that DFA? Does that mean like, if I get a string of length 1, that's the state, that's the configuration I can go to. If I get a string of length 2, those are the configurations I can go to. And then,
So the thing that you come back to over and over again. A state in the DFA is a set of states in the NFA.
right, I can get that, but what's like the more intuitive way?
A state in the DFA is a set of states in the NFA. There's no more intuition. This is it. You just have to understand this.
But why would you choose those states?
I don't know. It doesn't matter. I don't care. Every set of states in the NFA gives me a DFA state. Full stop. It may not be reachable from the start, in which case I can throw it away, and the incremental algorithm does that automatically. But
Incremental algorithm gives you all the states that are reachable.
that's right. Gives you all the DFA states that's reachable from the start DFAs.
So you stop when you don't see any new states.
That's right. That's
table. Okay. And the other question is, how do you formalize the idea of fitting an epsilon into an NFA? Because epsilon is really a string, but an NFA should accept the alpha.
You have to redefine what it means to accept. Okay, so you define you can define epsilon reach formally. The epsilon reach of a state is either the state itself or something that you can get to
For any state you can get to with an epsilon, you take its epsilon range. And so there's a formal recursive definition of epsilon range.
So is epsilon here an alphabet or a...
No, epsilon means the empty string. It means, so when you traverse an arrow that's labeled as a 1, you're only allowed to do that if you simultaneously eat a 1 from the input. When you traverse an arrow labeled epsilon, you eat an epsilon from the input, which means you do nothing to the input.
Those are arbitrary. Because there's
Those are
no
free.
epsilon.
Those are free. Yeah.
Just one question. So I know on the homework we're supposed to explain what every state in our automata mean, etc. If our automaton is constructed using this algorithm from a regular expression, do we need to then come up with an intuition of this state means we've seen this state? Or can we just say the algorithm said we need these states, and that's these states?
It depends on what the question is.
So for example,
If the question says, design a DFA for this language, I don't care how you come up with it. Come up with it by building a constant NFA and then subsetting it to DFA and then running the Hun good algorithm we talk about to get a regular expression. Okay, there's your regular expression, your answer. But what I want is an explanation. If, on the other hand, I say, tell me what the incremental subset construction gives you, then I just want the syntactic.
Okay, and you don't want an explanation of this state means this.
Right, because, I mean, it's not, I mean, I may just say, here is an NFA. No, I'm not telling you what it means. Execute the algorithm, you get a DFA. You can't really know what the DFA is supposed to do because you don't know what the NFA is supposed to do.
Okay, cool. Just making sure. Thank you.
Two things. One is kind of applying to one, two. And then also for the equivalent DFA with the new set of states, what is S in this case? No,
This is all subsets of Q such that subset intersect A is not empty. So I just needed a new variable here. I probably could have said Q prime.
okay, so that's just
It's just, S is just a set. It's a set of NFA states.
a set of NFA states.
Right.
So how's that different from just A itself?
A is also a set of NFA states. So, okay.
The point is, I don't see the intersection with the D typically.
Same as writing. My new set of DFA states. So, remember the rule for this. If one of my parallel states to DFA state, everything I reach. I mean, the DFA state is everything I reach in state 0. Finding the sequence of transition. Final state of my DFA is the set of all these NFA states. One of them is accepting. This is accepting. One of the states, one of the NFA states in S is also an NFA state.
So in this case, this Q is from the NFA.
Fine.
But so Q so the elements of Q are states, not sets of states.
Elements of Q are NFA states. I think it's actually useful when you're first keeping this out. Whenever you say the word state, always say NFA state or state. One of the things that makes us confusing.
Yeah, this is in this.
types are identical.
Okay, so how can we intersect it? This.
That. It's sorry. Like, no.
I think I just got a whole.
Yeah.
Just got a question about filling sets.
Okay.
Yeah.
Yeah, let me tear down here, and then I need to.
So you had a question about fooling sets?
Yeah. Because I saw this thing on the notes. So if you want to fill set of 0 to the 2 of power of n. Yep. Remember that. So you can use either the language itself or filling set, or you can use zero stop. Is that what you said? Yes. I was wondering why you can use zero stop. Yeah, zero stop contains the language.
Because for every pair of elements in 0 star, there is a suffix z, such that xz has length to the power of 2 and yz does not.
Oh. So
And
that's,
you have to. I mean, the fooling set by itself doesn't tell you anything. You also need to specify the distinguishing suffix.
yes, that's right.
Right, and so it's a somewhat smart-assy answer, but the reason I can use it for a fooling set is because every pair of things has a
So you can
distinguishing
construct
suffix.
it such that
Right, and